So far we've looked at trigonometry and how it applies to right triangles. However, we can use trig even if we're not dealing with right triangles. And the first way we're going to look at that is with what's called the law of sines. What I'm going to do is draw in an altitude from vertex B. I'm going to call that H. And then using this triangle on the left-hand side, I could say that the sine of angle A is equal to the opposite divided by the hypotenuse. And I have another triangle on the right, and on the right hand side, using just that green triangle, I could say that the sine of angle C is equal to opposite over that hypotenuse, so H over A. Now if I multiply this equation on the left by C, I get C times the sine of A is equal to H. And on the right equation that I have, I can multiply both sides of the equation by A. Then I have A times the sine of C is equal to H. Now the H doesn't change at all. It's the same little H from the same triangle. Using the transitive property then, I could say that C times the sine of A is equal to A times the sine of C. Which is kind of nice because at this point I only have two variables. I have C and A. Now they apply to the angles and the sides, so there's really four unknowns, but I only have two letters. I'm going to divide both sides by AC, and on the left-hand side it's going to simplify to sine of A over A, and on the right-hand side it's going to simplify to sine of C over C. And we could have applied this to angle B as well, so to extend this we could say that's also equal to the sine of angle B over B. Using properties of proportions, we could have also said that all of the reciprocals are true as well. In other words, A over the sine of A equals C over the sine of C equals B over the sine of B. And we can use this in any triangle regardless of whether it's a right triangle or not. The other equation that we can use is the law of cosines. And again, this doesn't have to be used on a right triangle either. To start this one off, I'm going to draw in this altitude, and I'm going to call it X. And I'm going to call this length little h, and since this whole side is little b, that means that this length is b minus h. What I've done is create a couple of right triangles, and I'm going to focus on this right triangle over here on the left-hand side. And because it's a right triangle, I'll say h squared plus x squared is equal to a squared. And if I solve this equation for x squared equals a squared minus h squared. So true statement, and I'm going to stick that in the back burner for right now. If I were to use the right triangle on the right hand side and also Pythagorean theorem, we could say that x squared plus the quantity b minus h squared is equal to c squared. Now using a substitution here, I'm going to rewrite this equation. Since x squared is equal to a squared minus h squared, I'm going to plug that in. So this x squared becomes a squared minus h squared plus quantity b minus h squared still equal to c squared. So I've got a lot of variables in there, and what I'm actually going to do is expand this out a little bit further. So a squared minus h squared plus, when I square this entire quantity, it becomes b squared minus 2bh plus h squared equals c squared. Using a little bit of algebra to simplify, I see that we have a positive and a negative h squared, and I'm left with a squared plus b squared minus 2bh equals c squared. And this equation is kind of nice because I only have little a, little b, little c, but I also have this lowercase h in there. So what I'm going to do is go back up to the original triangle and focus on this green side of it, this green triangle we have on the left. And using trig, I know that the cosine of angle C is equal to adjacent over hypotenuse. Multiply both sides by a, so h times the cosine of C, a times the cosine of C is equal to little h. Why is that important? Well, it's because I can make that substitution and plug it in for that equation, which leaves me with a squared plus b squared minus 2b times a cosine of c equals little c squared. And there is the law of cosines. Now this can be extended as well. I could have written this as a squared plus c squared minus 2a times c times the cosine of angle b equals little b squared. This is another equivalent version of that. And I could have written it in one other direction. Instead of having a and b or a and c, I also could have said that b squared plus c squared minus 2bc times the cosine of angle a is equal to a squared. So there's our third variation of the law of cosines. And both the law of cosines and the law of sines can be used on any triangle, regardless of whether it's a right triangle or not.